Uh, Good day, student. Today we are going to discuss about atomic scattering factor or atomic form factor. This is a subtopic of crystallography of solid state physics. And this parameter of solid state physics, particularly of crystallography, is a very important parameter because through this we can express the amplitude of the X-ray radiation scattered from an atom. Okay, and therefore this name is given atomic scattering factor. Here the scattering stands for the scattering of the X-ray. Okay. Now, now let us go to its definition first and its physical significance. Now, generally, what happens when X-ray radiation come, it interact with the atoms, and you see inside the atom there are nucleus as well as electrons, and the X-ray radiation mostly, now the extent of the electron cloud or electrons is much more than that of the nucleus. Okay, and therefore the interaction is mostly seen or realized from the electrons of the atoms. Okay, therefore this atomic form factor or atomic structure scattering factor is defined with respect to the scattering of an individual electrons. Now you see in an atom there may be large number of electrons. Okay, now you have to find out the total scattering amplitude due to this large number of electrons of the atom, and you have to divide these things with the amplitude scattered from one individual electron. Okay, then this ratio will give us the atomic scattering factor or atomic form factor. So therefore this has been mentioned in the first point here, the atomic form factor. I should have written probably a form factor, atomic form factor. F is defined as amplitude of the X-ray radiation by an atom divided by amplitude of X-ray radiation by electrons. Okay, so now you can see this from this definition you can find out its physical significance, obviously. So this is being mentioned in the point 2. It physically represents the amplitude of the X-ray radiation scattered by an atom with respect to an electron. Okay, now let us go to just deeper understanding of this through taking one example. Let's say one atom has atomic number is equal to Z. So then number of electron will be Z. Let's say this atom this number is, let's say 3 here, let's say. So the number of electrons is 3. Now I am representing this here in this picture. This is atom, let's say. Now here these are the electrons, let's say, and this is one electron here. Now the X-ray is, let's say, coming and hitting to this. Okay, and it is getting scattered in this direction. Now you see okay, now let's say scattering amplitude is A from each of these electrons. Okay, now the total scattered amplitude total will be Z into A. In this case Z is 3, so 3A. So the F should be equal to total divided by the individual electronic contribution. Now this is ZA by A, which is equal to Z, that means it's equal to 3. So the atomic form should be equal to then 3 ideally, but it's generally not exactly 3, it is just little bit less than that. Okay, this is mean mentioned here in uh, next point. Okay, now let us come to the expression of this. Okay, now mathematically this can be expressed by this integration, which is the integration with respect to the uh, a position r whose values can be represented starting from 0 to very large value infinite. Okay, let me give this equation number equation 1, and and it contains certain parameters like rho r, where rho r is the charge density of the electron cloud at position vector r. Okay, and here theta is the angle of not scattering, angle of, you can say, you can write down in better, glancing angle. Okay, with respect to, obviously you know this glancing angle is the angle with respect to the plane of this that is being defined earlier, you have seen. I can show you through a diagram here. Okay, generally while deriving this expression, it has been assumed that, so let me enclose this expression in the bracket. While deriving this expression, it has been assumed that the electronic cloud is spherical in nature. Okay, now and it is generally extending from the nucleus to a large value. Okay, it has been in this model it has been assumed that it has been extended to a large value, which is being represented by r is equal to infinite. Here r is equal to 0. Okay, this is the origin. Okay, the starting of the electronic cloud, it is extending to a large region over the nucleus. Okay, you see, so let's say this represent the nucleus. Okay, and you know the nucleus size is very small in compared to the electronic cloud. Now to give an example, the size of the nucleus is of the order of 10 to the 14 to 10 to the minus 15 meter, whereas size of the atom, this is nucleus, where the atom and the rest portion of the atom is occupied by the electron. So I can say atomic dimension is of the order of 10 to the minus n. This is the electronic dimension also, electronic cloud dimension. Now you see electronic cloud dimension is much larger than that of the nucleus dimension. Therefore, this electron density distribution can be assumed from 0 to infinite. Okay. Now in this region, let me consider a small electronic cloud region here, which is at a distance r. Okay. This is the position vector of the electronic cloud that I have considered. Now let's say my X-ray radiation come and a parallel beam of X-ray come and hit to this atom. Okay, now when it is hitting, it will hit to each portion of the electron, but for the simplicity I will consider the electronic X-ray ray. Parallel beam means a number of parallel rays. Collimated beam of X-ray I am considering, so that means a number of parallel ray. Okay, and I am considering two parallel X-ray. So this ray now are scattering in this direction. One is in this direction, another, and now these two scattered radiations will superpose and give us this superposition give us the expression for atomic form factor F. Okay, now here if you consider this is as plane of incident, then this angle is your theta. okay, which is being mentioned here. And r, I told you, r is the position vector at which the charge density is rho r. Okay, now if you take this small region having volume dv, and total charge will be rho dv, and then you can easily find out the what is the phase difference between these two charge region here and region here. And by using the uh, Laws theory, you can find out the scattering factor. Okay, and this generally comes in this manner as equation 1. And I have not dealt with this expression because it will take around 20-30 minutes, but I have given you a reference. You see, this reference contains the beautiful lecture of derivation of this expression. Okay, so please refer this YouTube video, and just go for this. It's very clear, very well explained, this derivation. So it's not necessary for me to do this derivation. Rather, I will focus on the use of this form factor. Particularly, this form factor, atomic form factor, is used to find out the total intensity of the radiation scattered from a unit cell of the crystal. Okay, that part, by looking that X-ray scattering from unit cell, you can recognize the type of unit cell and other things. That part will be discussed in the next lecture, in the topic called geometrical structure factor. Okay, so till then we can wait, but remember, to know whether you have understood this concept today or not, I have kept 2-3 questions for you, and that question you have to reply. Okay, so thank you.